therefore, is there such thing as an ideal gas? I ask this question all the time. Is there such thing? There's such thing as an ideal gas, true or false? Is there such thing as an ideal gas? Does an ideal gas exist? No, an ideal gas does not exist, right? It can't. Okay, number two, what makes an ideal gas ideal is there's no intermolecular attractions or repulsions, no intermolecular forces. There are intermolecular forces between atoms, particles, molecules. They could be weak, but they exist between all particles. And so this is false too. So if both of these are false, then why do we even bother with an ideal gas? The reason we bother with an ideal gas is because if we ignore these two things, it's going to lead to an error. But how big is the magnitude of that error? If the magnitude of the error is very small, then it's worth it. Because the little bit of error that assumption or those assumptions introduce means the math is much, much simpler. But if the errors are significant, then that's going to cause us trouble. And so our job is to know, when we can use the ideal gas law with some confidence and when we probably shouldn't use the ideal gas law. In other words, I used to think that gases are so easy. Gases are so easy because P equals nRT, P1V1 over N1T1 is equal to P2V2 over N2T2. It's so easy. That's what I thought. And then I realized gases aren't so easy. Because you know what? I didn't realize that the equation is wrong. Inherently wrong. I thought the equation was right. I thought I got the right answers each time I did that calculation. Okay, so you get the wrong answer, but how wrong is that answer? That's the thing, because on the one hand you could say, okay, that's all wrong, every single answer is going to be wrong that I calculate, but it's not true. And so what makes it difficult is you have to figure out, if it's a good calculation or if it's a bad calculation. And so the example I give is this. This is a question I ask all the time on tests. And so the example would be, let's say N is just 1 mole. P is just 1 atmosphere. And T just 25 degrees C. And so we calculate the volume. And so I calculate the volume of O2. Let's do that. And I get 24.45 liters. And then I calculate the volume of H2O gas. So I'm collecting H2O gas and O2 as a mixture when you collect gas over water. And this one comes out to 24.45 liters, the same. If both of these are the same, let's say, N equals 1, actually, same for both. Let's just say same for both. Are both of these calculations correct? Do you see any problems with this calculation? Nah, it's simple calculation, right? And you just plug it into the equation. Both calculations look correct to me. In fact, this is the number I asked you to memorize, right? Nothing wrong with the calculation. Okay, but comment on these calculations for me. What can you say about these two calculations? What I could say about these two calculations is this one I would think is pretty accurate. This one, not so accurate. This one accurate, this one not so accurate. Why? Yeah, because water molecules. Water molecules have hydrogen bonding interactions. Hydrogen bonding interactions are some of the strongest intermolecular forces, right, that you've learned. There's stronger ones like ion dipole, but one of the stronger ones, right? And so, versus O2. O2, they're just London forces, dispersion. There aren't strong, really, really strong intermolecular forces. We can get an idea of how strong the intermolecular forces are by seeing how long a gas stays a gas. You know, how close to 0 Kelvin can we get? You recognize this graph, it's volume versus temperature. Did I do this right? Yeah. Volume versus temperature. An ideal gas should behave what way in this? This is Charles' law. How should an ideal gas behave? An ideal gas should stay gas all the way down to 0 Kelvin. 0 Kelvin. And so ideal gas, you want to stay gas and behave this way down to here, but we know that something happened. What happens here is well above 0 Kelvin. When I get to 273 Kelvin, something happened. Actually, 373, sorry. When I get to 373 Kelvin, something happened to my H2O gas. What might happen? 1 mole of H2O gas is going to happen. Yeah, state change. In fact, at 373 Kelvin, the H2O is going to liquefy. Now it's a liquid. And so we go from a gas to a liquid, and then from a liquid to a solid. Right? So it doesn't even stay a gas. Whereas O2 will stay a gas all the way down to the 70s. Around 70, I forgot what it was, 77, 76 Kelvin, I think, O2 will liquefy. So this O2 doesn't stay ideal, but O2 stays pretty ideal. O2 is one of the more ideal gases, right? What do you think is the most ideal gas that you can think of? Yeah, one of the noble gases. Let me give you two choices, helium or xenon. Helium or xenon? Helium. Helium is much more ideal than xenon because it's not because it's lighter. Well, that's one of the reasons. It's lighter, meaning that the intermolecular forces are going to be weaker, but it's not because of its weight, it's because of how many electrons it has. And London forces depend on how many electrons it has. So lighter atom, we can infer, has fewer electrons, which means weaker intermolecular forces. And so one, the intermolecular forces are weaker because the dispersion forces are going to be weaker. And number two, helium has a much smaller volume. Helium's volume is closer to 0 than xenon's volume. Xenon's a much bigger atom. And therefore, helium is going to be the most ideal gas, but helium is not 100% ideal either. Helium is the most ideal gas, but when we get down to 4 Kelvin, at 4 Kelvin, do you know what happens? At 4 Kelvin to helium? No, it still moves. At 4 Kelvin, helium gas will liquefy. And we'll get liquid helium. And so helium almost makes it, but doesn't quite. And so the most ideal gas we have on the periodic table, that is helium, which liquefies at 4 Kelvin. Well, oxygen is not too bad. It's fairly ideal. In fact, nitrogen, oxygen, you know, the gases that make up air behave pretty ideal. How do we know? Well, we can do the calculations. We can calculate it for non-ideal versus ideal and see, well, we get essentially the same answer. The volume is going to be 24.45. Whereas if you calculate it for water, you're going to be off a little bit because the intermolecular forces are quite strong in water. So the volume is going to be in error. The volume we calculate based on ideal versus the volume we calculate based on this. And so this one is, I have more uncertainty, right? More uncertainty because it's not so ideal. Well, how do we handle that then? What should we do about water? Well, there are a whole bunch of things we could do about it. But what we're going to do is we're going to use an empirical equation that corrects the ideal gas law for these deviations from ideal behavior. There are 2 deviations from ideal behavior. What are they? Two deviations. What are they? Did you guys write them down? Number 1 was. Number 2. I mean, what I just had on the board. Well, anyway. Basically, we can see how these 2 deviations impact ideal behavior by looking at something called the compressibility factor. Compressibility factor just shows easily, you know, how things deviate. Compressibility factor is this. PV divided by nRT should equal 1. PV divided by nRT should equal 1. And so a compressibility factor of 1 is ideal. This dashed line shows a compressibility factor of 1. We look at hydrogen. Hydrogen's pretty ideal. You know, hydrogen and helium are 2 most ideal substances off the periodic table, we know, right? And so hydrogen's probably quite ideal. Oxygen, CO2 deviates much more. But the thing is, when I look at this, all of them deviate significantly. All of these deviate by huge amounts from ideal behavior. And so, you know, technically, should we even be using the ideal gas law for any of these calculations? Because look at the deviations. You would expect that the compressibility factor should be 1. And then we know, hey, that's decent. Oops, I didn't want to do that. That's decent. Oops. But you gotta look at the scale here. When you look at the scale, look at the pressures. Take a look, 200, 400, 600, 800, 1,000 atmospheres. How often are you gonna be working at 1,000 atmospheres? Never. How often are you gonna be working at 200 atmospheres? Never, probably. We're gonna be working at around we're going to be working at around 1 atmosphere. At around 1 atmosphere, are there huge deviations? No. And so number 1, at very high pressures, you know, greater than 5 atmospheres or 10 atmospheres, you better be using something else other than the ideal gas law. Because if you're using an ideal gas law for a pressure of 100 atmospheres, let's say the pressure is 100 atmospheres, and you want to calculate the volume using V equals nRT over P. No, that's not going to work. It's not going to work because deviation is too great. At 100 atmospheres, look at it, how much these deviate. Huge amount, especially CO2. At 100 atmospheres, CO2 is way off. So an ideal gas law calculation for CO2 at 100 atmospheres is worthless. All right, then what else? Well, there's two factors going on here. One, do you see the dip and then an increase? Here, dip and then an increase. There are two things influencing the compressibility factor. Those two things are intermolecular forces. Well, the first dip is caused by intermolecular forces. CO2's intermolecular forces of attraction are much stronger than O2's, and so this initial dip comes here. As the pressure increases to extremely high pressures, then another factor influences that. Hydrogen's intermolecular forces are very weak. The other factor that influences is the volume of the particles themselves, because look at the mean free path. The mean free path in air was only 68 nanometers, right, 10 to the minus 10. That would be 680 angstroms. 680 angstroms, the size of the molecule is about an angstrom. And so as the pressure increases, what happens to the volume? The volume gets smaller, the mean free path gets smaller. Pretty soon, the molecules are very crowded inside the container. The molecules being very crowded in the container, then this is it. When somebody says they have 1 liter of gas, you know, how much room is there for a gas particle to move in a 1 liter box? So if I have a 1 liter box here, these pens are. One decent pen. If I have a 1 liter box here and I have one particle, that particle pretty much has the whole 1 liter to roam free in, right? And so we would say the volume of the gas is 1 liter because that pretty much has a full 1 liter of space. But, you know, as the pressures get higher, you know, one thing that could happen is you pump in more molecules in there. Another thing that can happen is you just get a smaller box. Let's go for a smaller box here. Or both, you know, let's do both. Actually, I don't want to do both. I want to keep it at 1 liter, sorry. As the pressure increases, is there still 1 liter of free space to roam around in? You know, this is like saying, okay, you have like an acre of ranch land and there's 1 cow there grazing the ranch land. But if you put, you know, 1 million cows onto an acre, there's not going to be any room. It's not even going to be neat. This is the same thing. If this is so crowded in this 1 liter, then do these particles actually have 1 liter of free space to roam around in? Not at all. In fact, the volume of the gas, which is, you know, is actually what we say less than a liter. You know? Because the volume is going to be less than a liter because there's not 1 liter. And so you think, hey, the gas, when they think about volume, well, think about what an ideal gas is. An ideal gas is 100% empty space. Why? Because number 2. Number 2 says the volume of an ideal gas particle is 0. And so we're looking at the empty space. Well, an ideal gas has all empty space, 100% empty space. But is this going to have 1 liter of empty space? Not even close. The amount of empty space here is way below 1 liter. And so here you can see empty space is at a premium here. Everything's getting compressed together. And so these two have countering effects. One, the intermolecular forces of attraction cause the pressure. We'll look at just the pressure. One, intermolecular forces of attraction cause pressures to decrease. Because if this were going to hit the wall here and there's another molecule here, that intermolecular force of attraction would slow down that molecule by pulling it back. And so that's going to lessen the force of the collision here. And so IMFs decrease pressure, whereas the volumes increase pressure. And so these two effects can actually self-cancel. You can see that here. The IMFs are exactly canceled by, the decrease in pressure by the IMFs is exactly canceled by the increase in pressure from the decreased volume. And so at this point here, coincidentally, the ideal gas law appears to have worked because we get the correct answer. Right? And the same thing here. But this is like the broken clock. Broken clock is right twice a day. Well, the ideal gas law will be right. The conditions so happen. Although it didn't work for hydrogen. And so what they do is they just they take some measurements and they mathematically fit this behavior with an equation. There are multiple equations available. One equation is called here you can see what happens with the empty space. The empty space is shown in this magenta color. Now you can see the empty space is not much. Definitely not even close to the full volume of that. And so finite molecular size. Here you can see the decrease in the pressure due to the hindering of the collision here by these other three molecules. So we could fit this to this equation here. There are other equations in addition, the Beer-Real equation, etc. This one's called the van der Waals equation. And the van der Waals equation just adds two corrections here. One correction is to the pressure. One correction is to the volume. And so let's take a look at the pressure correction. If we look at the pressure correction, rather than P, we do P plus this, AN squared over V squared. What's this correction? The bigger this correction is, the bigger the pressure? No, the bigger this correction is, the smaller the pressure. And so what do you think this correction is? Is it due to IMFs or do you think it's due to volume? The bigger this correction is, the smaller the pressure, the lower the pressure. And therefore that correction must be due to IMFs. Right, IMFs will decrease the pressure. And so the term here is A. A is just empirical constant, N is the number of moles, V is the volume. And so what we do is we look at, basically we look at the concentration of molecules and A. A, you know what A is? A is kind of the strength of the intermolecular forces of attraction. So let's take a look at A in detail here. An ideal gas is going to have an A value of 0 because there are no intermolecular attractions, no IMFs, no intermolecular forces. Helium is the most ideal gas with an A value of not 0, but 0.03, 46. Very small A value. What is the least ideal gas and what is the A value? Can you see what the least ideal gas is in this list? Propane is the least ideal gas. In fact, when you buy propane, from the store, it's a liquid. It's not even a gas. And then you open it, and then the liquid vaporizes into a gas. And so propane is 939, which means, you know, it has fairly strong intermolecular forces. Now you think, well, why does propane have strong? Isn't hydrogen bonding the most important? No, it turns out that it depends on how many electrons you got, because the dispersion forces can exceed hydrogen bonding interactions. Because if you look at, let's say, do we have ammonia? If we have ammonia here, ammonia has hydrogen bonding interactions between ammonia molecules. That's only 4.225. But, you know, the bigger the molecules, you know, even though this only has London or dispersion forces, if we think about things like wax are just these big alkane chains. This, you know, when you get to very long chains of hydrocarbons, they become solids. Asphalt is another example. And so those can have very strong intermolecular forces based on the sheer size of these things and the sheer number of electrons. But anyway, here we can see going from ideal to non-ideal in terms of the IMFs. Okay, the units are weird here. This is in bars per liter, bars liter square per mole square. Okay, the next correction that we are going to do is to the volume. Volume is going to be minus n, which is the number of moles in B. You know what B is called? B is called the molar volume, but it's not the molar volume of the gas. It's the molar volume of the particles themselves, you know, excluding any empty space. So it's the actual volume of the particle per mole of particles. And so you might have a liter of water, but the molar volume of particles in that liter of water is not 1 liter. Because even though, let's say I have this bottle, and let's say I have about 50 milliliters of water here, this 50 milliliters of water has a lot of empty space between the water molecules. We ignore that and just look at the size of the volume of the molecules themselves, ignoring all the empty space. And so that's what B is. And so let's take a look at B here. All right, B for an ideal gas is going to be 0, you know, because the particles don't have any volume. And this is in liters per mole, so it's going to be very small. And so if we look at something like liquid nitrogen, or not liquid, because liquid nitrogen would actually have a bigger volume than this. Again, because there's empty space between the nitrogen molecules. This is just the volume of the nitrogen molecules themselves, which would be 38.7 liters per mole of volume. I mean, 38.7 milliliters. 38.7 milliliters, this is significant volume. And so if I take a mole of nitrogen and measure the volume of each of those molecules, we got 38.7 milliliters. If I take a mole of nitrogen gas and liquefy it to get liquid nitrogen, the volume would be greater than this because the nitrogen molecules can't occupy 100% of the volume. It's like packing oranges into a box. There's going to be empty space between the oranges. Well, take a look. The smallest, obviously, is going to be what on this list? Is helium. And therefore, helium is pretty ideal over a wide range. And then hydrogen, and the biggest will be propane. And so we got to be careful. You know, we have to be careful looking at these. And on the last column here, we have the compressibility factor here. Let's see. But the compressibility factor changes, so we've got to see how that was calculated. I'm going to ignore that. And so we could do calculations to find out, you know, this is just equal to nRT. This is a hassle. The reason we don't do this for every gas is because if we're doing a calculation of 1 atmosphere, then at 1 atmosphere and room temperature, most gases behave close enough to ideal, right? at 1 atmosphere and room temperature. Most gas. And so at 1 atmosphere and room temperature, it's such a hassle because for every single gas, you have to find A and you have to find B and do separate calculations, right? It's a hassle. And so if we can assume that most gases behave ideally under ambient conditions, then it's much easier to use PV equals nRT. But when do gases start to deviate from that? Well, gases are going to start to deviate as the temperature goes lower. Gases tend to behave non-ideally at low temperatures. And so low temperatures, obviously certain things can happen. It might not be a gas anymore because it liquefied too. But also at low temperatures, the molecules are moving slower. As the molecules move slower, intermolecular forces of attraction become more significant. If the molecules are moving at 1,000 miles an hour, you know, intermolecular forces of attraction aren't. But if you slow them down so that they spend more time, then those attractive forces become more significant. And high pressures. High pressures, you know, gases should deviate at high pressures because volume. You're packing more molecules or particles in there, the volume isn't going to be. Okay, now here comes the problem. The problem is, what is low temperature and what is high pressure? There's no fixed number for that because it varies depending on the gas. So for example, helium, you know, helium at 0 degrees C, is that considered high pressure? Well, I didn't tell you the pressure. But 1 atmosphere, is that considered high pressure? No. 1 atmosphere is not. What's considered high pressure? What's considered high pressure? Well, looking at this compressibility chart, a high pressure would be starting around what? 5 atmospheres, maybe? 10 atmospheres? You know, right at the beginning here. Then when you get to like 100 atmospheres, whoa, you're way out there, right? And so low pressure is considered here, high pressure is considered everything else beyond this. And so 2 atmospheres, is that really high pressure? No, you're probably still okay. Okay, so pressure is easy because pressure is here, but temperature is not easy because temperature depends on the species itself. And so 0 degrees C for helium is high temperature. Is 0 degrees C for water vapor high temperature? No. And so you have to have some kind of judgment on this, you know, based on, well, how do you base it? Well, you base it on prior calculations you've done or seen. But temperature is going to depend on what the species is. Obviously, the stronger the intermolecular attractions, the higher the temperature we're going to need in order for it to behave ideally. The weaker the intermolecular attractions, then we don't really worry too much about temperature. We can go much, much colder. For example, helium can behave fairly ideal to very, very low temperatures. Right? And so the calculations for helium are going to be quite accurate, whereas the calculations for water are going to be off a little bit. So let's say you want to do some calculations using this. Well, to calculate the pressure is not too bad. If you want to calculate the pressure is just equal to nRT over V minus MB. So you look up B, you figure out N is the same as this N. You look up A in the chart, and we know what N and B are, and then the calculation is not that difficult. It takes a little more time than, you know, P equals nRT over V. P equals nRT over V is a very quick calculation, right? Now, if we did a calculation using this for helium versus the ideal gas law, the answer is the same, essentially, at least to the number of sig figs that we do. If we do it for propane, under ambient conditions, 1 atmosphere and 298 Kelvin, versus the ideal gas law, nRT over P, we're going to be slightly, nRT over V, we're going to be slightly different, right? But not significantly. We still perhaps use it for both, right? You're going to do calculations and compare. So you do the calculations and compare. So that's not too hard to calculate the pressure. Pressure using the ideal gas law versus the pressure using the van der Waals gas equation. Again, this is an empirical equation, and those are empirical corrections. But what I want to do is I want to do something harder. What I want to do is I want to calculate the volume of the gas. And so let's say I want to calculate the volume of propane. Let's say I went out to fill my cylinder. I got say a pound of propane. So let's calculate the volume of propane. We got 1 pound of propane. And it's in the cylinder, it's compressed, it's a liquid, right? It's easy to measure the liquid masses, right? You just throw it on a balance. Say I got a pound of propane. But that liquid is going to vaporize into a gas. And so I want to figure out, how many liters of gas did I just buy? If I got 1 pound of propane. And so, okay, that's fine. 1 pound of propane, let's figure out the volume equals what at, what should we do? You know what I'm going to do? I'm going to do this in bars. I'm going to do this in bars because A and B are in bars. That table's for bars. And so at 1 bar, well, 1 bar, that's close enough to atmospheric pressure because anyway, atmospheric pressure is fluctuating day to day, right? And so we're just going to use 1 bar. 1 atmosphere is actually 1.01325 bars, right? But we're close enough. At 1 bar, and this is to make the calculation simple, and 298 Kelvin. All right, so anyway, propane's CH3, CH2, CH3. CH3, CH2, CH3. So I have 3 carbons. That's 3 times 1201, which is 3603. And then 8 hydrogens, 8 times 101, which is going to be 808. And that gives us a molar mass of 114411. So we'll just do this using dimensional analysis, ignoring sig figs. We'll just say I have exactly 1 pound of propane. If I have exactly 1 pound of propane, then converting this, we know that there are going to be 2.20 pounds per kilogram. That gives us kilograms of propane. Then 1,000 grams per kilogram gives us grams of propane. We want moles. So a mole of propane weighs 44.11 grams. And so this will give us how many moles of propane we have. How many moles of propane is it? So one can calculate it. So again, I just bought 1 pound of liquid propane. I want to figure out how many liters of gas it is. Usually you get much more than a pound. 10.3048 moles of propane. Propane is C3H8. All right, so the volume is easy. The volume is propane gas.